So this is something that we got quite excited about because it's used everywhere. This is contrastive pre-training. It's used in all the kind of modern machine learning models. It's a huge investment, like tens and tens, maybe hundreds of millions of dollars of just compute to actually carry out the computations. And very little is understood about it. So we got interested. We thought, okay, well, let's see if we can understand something. So this is joint work with Kiril Bangachev, who's sitting right here. So any questions, ask him right after this. He'll be around, I guess, off and on during the week, as well as Iliyas Noman and Yury Polyanskiy, who probably all of you know. Okay, so what are we talking about when we say contrastive embeddings? Let's see if this remote. What the heck is contrastive pre-training? I keep using this term. I will continue using this term. It means multiple things, but for our purposes, it's going to mean the following sort of simple setup. Okay, so the basic idea, you have two sets of embeddings on the sphere in d dimensions. One embedding comes from an image encoder. You could think of it as the last layer in some neural net. A second set of embeddings comes from text, which again is something that's been processed by some large language model or whatever. And we'll denote UI, the image encodings, VI, the text encodings. Okay, these are just points, like a sentence gets mapped to a point, for example. And these are paired. For instance, images and captions. Most of the images on the web have captions, so this data is very prevalent. What do you want to do with all this data? Well, the high-level goal is that you would like to embed both of them on the same space so that the corresponding image and text are close to one another on the sphere. Okay, this is kind of a natural goal. So for instance, you want the embedding of the word dog to be close to the embedding of an actual image of a dog. All right, now one remark is that SigLIP, which I'll be talking about for the most part, a very popular model, has roughly 10 to the 10 number of these kind of representations, image text pairs. And dimension is only on the order of 1,000. Okay, so n here is way, way bigger than the dimension. And that will play an important role that I'll get into later. But for now, you can kind of remember that that's the realistic regime. Okay. Let me just say a few more details on this kind of setup. So we have the image representation UI. It's given by this f sub theta. I see. Oh, there we go. The image is given by f sub theta. VI is given by g sub phi. So these are some trainable neural nets. And the rough idea is that you're going to minimize over these parameterizations of so-called contrastive objective. So that's something that is going to encourage similarity between image I and caption I, those embeddings. Okay, so you're minimizing this distance, and then you're going to maximize the distance for I not equal to j. So here's a sum over I not equal to j, and we have the distance between an image I and then mismatched pair caption j for j not equal to I. Okay, so this is kind of what people think of when they say contrastive loss. You're optimizing something that looks like this. Now, you're optimizing over the parameterizations of these neural nets, phi and theta. As we'll see later, that neural net structure doesn't play a huge role for our analysis, but that's kind of how things are actually done. All right. Please, yeah.
Is the same distance for either sum, or?
For now, let's just keep it loose. I'll write a few concrete things that'll make it clearer. Yeah, it's essentially, but it depends, I think is the answer. Okay. Yeah, I'll skip this remark now. Okay, so this sort of contrastive loss setup has been immensely popular for a long time, actually, before the modern era, let's say, in various contexts. And so one context is in self-supervised learning. So the idea is you have an image, and instead of captions of images being the kind of corresponding other object, you might just have a bunch of noisy copies of the same image. You might even produce it yourself. So that's a natural self-supervised setup. I have an image, I noise it in like 10 different ways. So obviously these all correspond to the same image, and now I can train representations that are going to send all of these to nearby points. Recently, this whole pre-training notion became very exciting for folks when they realized that this sort of thing actually can lead to better representations than supervised learning with labels. And it's sort of free in terms of the data. It's just kind of sitting out there. This got even more exciting with CLIP, BLIP, Align, and various other kind of massive industrial scale contrastive pre-training setups. Exactly in this kind of text image situation, CLIP was OpenAI's model. You can go even beyond two modalities, and this is one of the kind of latest developments where this is being used. You might have audio or speech waveforms, you might have text, images, and also video. You might have various other things as well. And then you somehow want to embed all of these on the same space and use them in some productive way for downstream task. So this sort of contrastive loss is useful there, and we'll talk about these multimodal setups kind of at the very end. All right. So why in the world do you want to do this contrastive pre-training? Well, some of it I've hinted at. At the most basic level, it seems to improve the embeddings you get. So even if all you care about is images, having text there seems to give rise to better image embeddings. And that's a quote from Philip Isola at MIT, who says exactly this, that somehow there's information contained in these other modalities that actually leads to better representations, even if all you care about is images. So it's a good idea. It's useful for many downstream tasks. For instance, you want to produce a caption for a new image. You find the embedding of the image. You find some text that's embedded close by to that, and you could use that potentially as your caption. And there's a bunch of other uses that are somewhat less obvious. For instance, distillation. I have some big complicated model. I have some little model. I might want the representations produced by the little model to somehow be close to those produced by the big model, and that might give rise to a good little model. Okay, so those are just a few of the reasons why you want to do this. There's actually many, many more reasons. It's kind of mind-boggling how useful this is. There are many questions about contrastive pre-training or contrastive loss. First of all, which contrastive loss to use? This gets to maybe Jason's question, like what do I actually want there? What do the trained embeddings look like once I've chosen a contrastive loss? What do we want them to look like? Maybe those aren't the same. How do you choose various hyperparameters, dimension, and so forth to go into the way that you're doing this, and so forth? There's many other questions. All right, so we're not the first to ask these questions, maybe obviously, given the popularity of contrastive pre-training. So I'll mention a few results first that exist already for InfoNCE, which is a very popular loss. This is what's used in CLIP, which, as I mentioned, is OpenAI's model. So what is this loss here? We have basically a term here that encourages UI to be close to VI in the first part here. That has a minus in front, so you want to make this thing big. So UI close to VI is good. And then this one also wants to make UI close to VI, and where UI wants to be far from VJ is what's in the denominator. That's this normalization. Okay, and you can also just think of this as a softmax, essentially, of U transpose V, and you kind of arrange things into matrices. So here's one result. If n, remember that's the number of these UI-VI pairs, is less than D, okay, so this n is less than D, then explicitly the global minimum of InfoNCE loss is given by setting UI equal to VI. So you fully just collapse those representations, which is sort of natural. Text and image embeds precisely to the same point, and U1 all the way to UN are the vertices of a simplex. Okay, so that's one result. In the completely opposite regime, when n goes to infinity, number of points goes to infinity, a result of Isola shows that the measure of the points, if you look at the kind of discrete measure, it converges to, again, UI equal to VI. So again, the representations collapse, and they're now uniform on the sphere. Okay, so this is most of the theoretical results for InfoNCE in terms of what sort of objects we get. There's results for sigmoid loss. I'll tell you in a second what sigmoid loss is. I'm not writing it here. Again, when n is less than D, there's a simplex structure, but here it's a little bit more intricate. So here, W1 through Wn are going to be the vertices of a simplex. UI is going to be essentially that thing, but then with a extra little final coordinate. And then VI is going to be that same simplex point, WI, but with minus in that last coordinate. So in this case, the global minimizer of sigmoid loss, which again, I'll tell you what it is in a moment, in this regime of n less than D, are kind of UI and VI are separated by a little bit. Okay, and this construction is going to play a role in some of our results as well. So we'll see it again in more depth. Please, question.
Yeah, so sorry, so just out of curiosity, so when n is less than d, can you characterize that simplex? Because if you could, then I guess there's no point. You don't even have to do the optimization, so.
You don't have to do the optimization.
So it really-
Yeah,
n greater
you
than
can just write down. You can just write it down. Yes.
So
Yeah.
n greater than d is actually,
Sorry, n less than
sorry,
d is easy.
the n greater than d is actually the setting where
Good.
you can't do this. Yeah.
Perfect.
Yeah.
So what about the regime when n is bigger than d? So now, of course, n is bigger than n is d plus 7. Okay, already this is not applicable. But as I said before, I mean, n was 10 to the 10 for SigLIP and d was 1,000. So we're talking about completely different scales. So that's the situation we care about. And obviously none of these results, except for maybe this one, is relevant. It actually turns out that weird things happen in the limit where n goes to infinity. So it's unclear that that's actually the relevant regime either. Where exactly this n goes to infinity kicks in seems to be exponential or much more even than exponential. We won't actually say anything about influency anyway, but that's maybe some intuition.
Does d go with n?
Here?
Yeah.
I mean, we're thinking of d as fixed.
D is fixed.
Yeah, exactly. So it's a truly like n go to infinity limit with d fixed. Very good question. I mean, you would want to study this with both scaling. Well, yeah. Okay, and then another kind of question, which is, sure, we want to understand some of these results, but in the actually practical regime, there's all sorts of very interesting phenomena that occur for trained representations in the real world. And we want to understand, can we explain those? Can we understand those? So forth. Question, please.
Any description for local?
Sorry?
Any description for local minimizer?
Well, a global minimizer is a local minimizer. But there's kind of nothing outside of this that we're aware of in terms of local minimizer either. Yeah, it's a good question. Yeah. Yeah, good. Okay, so can we understand properties of actual trained representations? What sort of property might we care about? So I'm gonna describe a mysterious property of actual learned representations. And so to get a sense for this, remember that the training, and this is maybe kind of especially obvious if you look at the info NC loss that we saw, pushes UI close to VI, right? They're trying to align those representations. And so eventually UI should equal VI, it seems, for every I. And indeed, the theoretical result that I mentioned says that that is the case in the limit n goes to infinity. But intriguingly, it turns out that that is not the case in practice. And there was this quite comprehensive paper that showed that across many different situations, many different modalities, in commercial, industrial size models, the UIs actually sit in a completely disjoint part of the space. So here's CLIP, and here's the UIs, and here's the VIs, and those are completely separate. They're in different parts of the space. Now, that's not just true for CLIP, it's true for video clip, and it's true for numerous others. Here's just a few sample that we took. This is quite a mystery. So what's going on? Well, people were very interested to try to explain what's going on, and there were many theories. One theory was that maybe it's these different models. So here we have natural image and text. I mean, those are different models, different architectures. Maybe that's leading those things to just get pushed separately. There are many other possible reasons, mismatches in the data sets. I mean, who knows? All of those reasons were definitively debunked on the empirical side by this elegant experiment from a year ago, which actually trained InfoNC with precisely the same architecture, same initialization, same everything, and they got the same sort of picture. So this picture, by the way, is called a modality gap. The text is one modality that's separate from images and so forth. So this modality gap is not caused by difference in encoders and so forth. Okay, so what in the world is causing the modality gap? Is it something inherent in the contrastive loss? And if so, what is going on?
So can I just to understand the picture? So like this is, you take high dimensional representations and you took some low dimensional projection of them, which you computed using, I guess, your UMAP coordinates.
Exactly.
And
Yeah.
Is the interesting thing that there's just that clear separation between blue and red? That length is big in some appropriate sense of big.
That's right.
I don't know what the units are, kind of.
Yeah, that's right. I mean, the fact that you can even put a hyperplane and there's a separating hyperplane that separates them completely is already remarkable. It's sort of non-obvious a priori. It would certainly not be the case if UI collapsed on a VI in any sense. Right. And so that's a good question, the size of this gap. How big is it? Why is it a certain size and so forth? Certainly, very interesting questions. But even the existence of such a separating hyperplane is already remarkable.
Okay, and just one more stupid question. I promise I'll shut up after. Like,
No, the questions are great.
When you wrote down the objective function,
Yeah.
like you wrote it as the sum over like kind of positive pairs minus the sum over the negative pairs. Like you didn't normalize them differently. There are many pairs.
Yeah, very good. Yeah.
So like that would be a reason why like just pushing things apart might like have more kind of power.
Absolutely. Yeah. Yeah. I mean, there's all sorts of intuitions for why you might expect this. Yeah. Yeah. So somehow in retrospect, it's not that surprising that things are getting separated, but it's also not obvious that it should, I think. Maybe Kiril has more to say on that, but absolutely. Okay. So good. So that's one of the things that's kind of these burning questions that, we'd love to say something about. Like I said earlier, we're going to focus on SigLIP, Sigmoid Contrastive Loss. This is a model developed by Google DeepMind a couple of years ago. And at the kind of most superficial level, there's this quote from Hugging Face where you can download SigLIP, which is that SigLIP is CLIP, but it's just way better. And for various reasons. Okay, so it's better because there was that normalization term in CLIP where you had like the sum over I not equal to j, and you have to do that over your whole batch. It's very computationally expensive. It's a pain in the butt. In contrast, here's SigLIP, and this is very much of the kind of generic form that we saw before. So what is going on here? You have, oh, I see. My pointer doesn't do anything. I've been like pointing at things, but it doesn't show up there. Well, that's totally fine. I'll just point with my arm. So we have something that sums over UI and VI, which is encouraging them to be close, right? If that inner product is big, then what's in the exponential gets small. And then there's a separate term I not equal to j, and this is encouraging these to be kind of negative inner products, or at least as small as possible. Okay, so this is a sigmoid contrastive loss, and you can see that they interact only pairwise. So computationally, you can take larger batch sizes and so forth. So there's various kind of engineering reasons that this is a good thing to do. It turns out for various reasons that even with the same batch sizes, it performs quite well and so forth. So those are things I won't get into. One remark is that here I wrote it as the minimum over the representations themselves, the UI and VJ representations. Of course, what's actually happening, as I mentioned before, is that you're optimizing over the neural net parameters. But for our purposes, much of the analysis can be just done thinking about the representations themselves. Okay. So let's get a feeling for this SigLIP model. So Kiril did an experiment on ImageNet. And so first of all, so we have 1,000 images and captions. The caption is, this is the image of a dog, or this is the image of a plane, or whatever it is. And here we have a histogram of the contributions within the loss. So here we have mismatched pairs UIVJ, and these are relatively smaller inner products than most of the matched pairs UIVI, which is in some ways to be expected. And a thing to emphasize is that they're mostly pretty separate. Okay, so most of the matching pairs have bigger inner product than those that have mismatched pairs. And that's what you would hope for if you were going to actually make this thing small. This also has a modality gap, the SigLIP on ImageNet dataset. Here's a projection onto one dimension, and this demonstrates that there's a separating hyperplane where all of the text lies on one side, images lie on the other side. Right, so this modality gap is very much present for SigLIP. Okay. One of the things that I didn't mention about SigLIP, which turns out to be important for us and maybe important for everybody, is that the temperature and the bias are trainable. So the temperature is kind of the weight here, which says how important is it that the inner product is big or small. And the bias is just a shift inside here. So they're T and B. And those are actually trainable in SigLIP. And the effect is actually significant. It makes a real difference that those are trainable as opposed to just being some fixed thing. And here are some experiments that show that. These are some synthetic experiments where one representation, let's say text is, I guess image is probably, text is probably locked, image is trained, I think. And so here's a fixed very high temperature and zero bias. Here's a fixed moderate temperature and zero bias. And you don't get the separation whatsoever. However, with trainable parameters, we get this very nice separation between the positive inner products that are supposed to be positive and large and the mismatched ones that are supposed to not be as large. Okay, so we call this a margin. There's a separation between the positive inner products and the mismatched inner products. Okay, so let's visualize what's going on when we train this thing. So here's again our synthetic experiment in 3 dimensions, and we optimized using Atom, and it sort of does this. So initially you saw this like quick scrambling, and then it settled in to this representation. This looks like after step, I don't know, 1900. Okay, let's see if I can show that again. All right, so let's summarize what we're observing. There's a bunch of things actually that are going on in this video. So first of all, there is a modality gap. Here's all the text on one side and the images on the other, the separating hyperplane. There's a margin. The margin is slightly less easy to see from this picture, but again, what does margin tell you? It tells you that U1 V1 has a bigger inner product than U1 V3. Right, and that separation holds for every pair. And that's because this blue point is closer to this red point than any of the other, red points are to this blue point, and so forth. Okay, so this does have a margin. Turns out maybe there's some sphere packing if we just look at the slice where all of these blue points live. They're kind of nicely separated from one another. We'll get back to that. And then finally, the loss is 0 for this configuration. That you can just check. It actually comes from the fact that there's this margin. So the loss is 0, and that got us thinking. We thought, maybe we should study those configurations that have 0 loss. Here's that those are the ones that are actually arrived at when you train this contrastive loss.
What is loss?
Loss is this whole thing.
The whole.
Yeah.
Is that obviously bounded below by 0?
Is it obviously bounded below by 0? I believe so, because you have something positive here, and there's 1 plus maybe 0. So log of 1 is 0. Similarly here.
That's right. Okay.
Sorry, so is the other one, the other loss where you had like the
influency?
Yeah, is that bounded away from
let's see.
Convexity or something?
I don't know. Is it Kiril?
I guess my question.
We don't have any result for influence.
You don't observe the same kind of thing with that. And
our experiments do replicate most of what we've observed for SigLIP, but there are some differences. Yeah.
Answer is theory.
Yes. Slightly less obvious. Yeah. Okay. So then finally here's some results. Here's maybe a first result. Given that we're suddenly very interested in global minimizers, 0 loss configurations. So a training run converges to a global minimizer if and only if a bunch of things happen. So first off, the inverse temperature goes to infinity. That one's maybe obvious because at any finite temperature, you're just going to have some finite thing there. The relative bias converges. So what that means is that B here scales with T in a way that B over T converges to a constant. And the resulting constellation of UI and VJs satisfies what we call the MB property, or it's an MB constellation. And that's the following. So for any I not equal to J, their inner product is a little bit below this BREL, the margin. For matched pairs, their inner product is a little bit above BREL. And the gap is this margin. Okay, so here's the definition of margin, but it's maybe obvious already from there. And one remark is, I sort of forgot to mention I mentioned that you want the caption to an image. So you just find the text that is closest embedding to the image. How would you actually do that? You would do some sort of nearest neighbor search. And this property enables perfect recovery or perfect retrieval using nearest neighbor search, because this is exactly telling you that if I want the VI corresponding to a UI, it has a bigger inner product. It's closer than any of the other VJs, right? So this property corresponds to perfect retrieval, which is one of the primary downstream tasks that people care about when they produce such representations. Okay, so we have this constellation, zero loss, global minimizer, if and only if it's this MB constellation for some M and B. First question you would ask is, do these things even exist? It's maybe a priori not obvious. How large are they if they do exist? How big can N be in a given dimension, and a given B in a given margin M? And then finally, if we're really going to be ambitious and maybe greedy, can we say something about this modality gap relating to zero loss configurations? All right, so before we go more into the results, let me just go back to this ImageNet experiment and make some remarks. So the main thing is that, okay, these overlap slightly, but the point is it's a slight overlap. These are almost separated. They don't have a positive margin. This just tells us that this theory, this property, is approximately holding for actual data. Again, so this is not the modality gap. This is just the margin property. This is saying that all of the positive inner products are bigger than the mismatched inner products, right? But almost in the experiments. Turns out that the things that overlap are actually in some ways like almost unavoidable. Like here's an example of a kind of incorrectly matched pair that something wrong is closer. There's two different types of chameleons, it turns out. One is a African chameleon and American chameleon, and it's putting the image of one to the other. But this is a mistake that even a human can make, right? So it's not maybe a huge deal. So again, these are not egregious, like an airplane and a cat are getting confused or something. They're things of this nature. Okay. So back to our results. We said that the zero loss configurations were the things that are MB constellations. They were the things where the inner products have the separation property. And so here's a diagram depicting when they exist or not as a function of, here's the relative bias. So remember, this was B over T. And here's the margin, M. And so in this region, where the margin is not too big, so it's in this green region, there's constellations of exponential size in the dimension. Here, no constellations of a growing number of points exist. It's a stark gap between, there's a very strong separation between these two regions. So that's maybe a first kind of part of this diagram. If we zoom in a bit, we can place several popular models onto the diagram. And it turns out that they land in this part of the region where we can actually show that there is a margin, where we can actually show that there's a modality gap. And so I'll tell you more about the modality gap in a moment. But maybe this, at this point, is an interesting observation. I don't know that we know how to read something profound from placing these various versions of the SigLIP model onto this diagram. I mean, at least, let's put it like this: at least they're not landing out here. Then we know we did something horribly wrong.
Is it strange that the red ones go on the boundary? Like if they were all in the interior, it'd be like, okay, whatever.
Yes, this is a funny boundary. This is the boundary of what we know how to show has a modality gap.
Oh, so that's like an inclusion. So you definitely know there's a modality
Exactly.
gap.
We don't know how to show that there is no modality gap here. Probably there still is a modality gap, but it's not. Maybe we're not that confident. I don't know at this point. It's a good question. Does this particular location for these large models mean anything? I don't know. Yeah. All right. So how do we get this green region where there are exponentially sized configurations or constellations? Well, there's a connection to sphere packings. So a sphere packing is just a collection of points where the inner product between any pair of them is bounded above by alpha. So this is an error correcting code. For those who've seen that, there are bounds on how large they can be as a function of dimension. So if alpha is negative, you can only have very few such points on the sphere that are well separated because they can only have, like very relatively obtuse angle. For positive alpha, there are exponentially many. So it's 2 to the d, and then there's this exponent e of alpha. E of alpha remains a mystery for, I don't know, like 2/3 of a century or something. It's a central problem in combinatorics to understand E of alpha. But there are bounds on it, and that's sort of good enough. Now, given a sphere packing, we get an MB constellation. How do we get that? Well, it turns out you just directly get an MB constellation. So if you set UI equal to VI equals the point on the sphere, the code word, well, why is that immediately giving us an MB constellation? Well, the inner product between UI and VI is 1, so it's quite big. And then the fact that it's a code tells you that the other inner products, the mismatched inner products, can't be too big. They have to be at most alpha. And so that corresponds to a certain choice of M and B rel. Inside this definition, M plus B is 1 because the matched inner products are 1. The mismatched ones are alpha, so that's B minus M, and you get alpha. Okay, well, that's just one particular type of constellation where the UI is equal to VI, and these are perfectly aligned. They don't have modality gap. What about those constellations that have modality gaps? Well, we can introduce an additional coordinate here that sort of forces a modality gap. So for all the UIs, we're just going to add a little C here in the final coordinate, and then there's a minus C for the VIs. And so those are just going to sort of separate these two sphere packings. So C parameterizes the modality gap. B here is going to be responsible for a bias that we can kind of trade off between these various A, B, and C. And this construction spans all of the green region, right? So we started with an exponentially sized code on the sphere, and then we added a couple of coordinates, and we traded off between these, and this gets the whole green region. Okay, I won't talk about why no constellations exist here. It's not terribly difficult, but you're welcome to look at the paper for that argument. But this at least tells us that there are constellations that are very big, and those are the ones we want because N is much, much bigger than D. Okay. Can we say if, yeah, please.
Yeah, so sorry, I'm still, I guess, trying to understand whether you have this property for different regimes of like N and then the dimension of the U and the B's. Because I would have thought just intuitively that if N is really large and the dimension is fixed or small, that it would be harder to get these sorts of separations.
The sort of separation between U and V.
Exactly.
Yeah, well, one thing is that this isn't terribly costly. Like this separation is only happening in one dimension in this construction, whereas you have D minus 2 dimensions here for the actual code. So you're not losing like that much. Once it's exponential in D minus 2 is also exponential in D. Right, so it's not costing you that much to separate these things slightly in just the one dimension where you're choosing to separate them. Yeah.
But I guess I'm thinking of the pictures that you're drawing where kind of everything is like well separated.
But they're still separated along one dimension.
Oh, they're still separated along the one. Oh, I see. Okay, well,
yeah, like there's this picture here, right?
Yeah.
It's kind of faint, but right. So in like D minus 1 or D minus 2 dimensions, there's code, and then you shift it.
Got it.
Good. Yeah. Keep the questions coming. They're great. Yeah. Sorry. Either way.
In real embeddings, is there a way to estimate like what along how big of a dimension stuff like the separation?
The modality gap?
Yeah.
Well, we'll get to modality gap. So yeah, we'll get there. The modality gap is agreed. It's one of the most interesting things. But yeah, it's a very good question. Yeah, we'll see more, and then your question is great. Yeah, I don't entirely know the answer, but maybe we'll partially say something. Okay, so yeah, we just said exponential size constellations exist. Let's actually say something about the actual capacity N as a function of D. And this comes from this coding exponents that have been studied to death. So one can convert between the margin and the bias, and there's a corresponding alpha. And so one gets the following sort of curves that are upper bounds and lower bounds on this exponent in dimension. So, it's pretty good. These bounds are, at least they match here and they kind of match up there, and there's a little gap. Yeah. Okay. Right. So what about modality gap? Okay, this is this really fascinating phenomenon. Please. That's right. Yeah, perfect. Yeah, I mean, they're also for our specific construction. Yeah. Okay, so what about modality gap? Well, we have the following result. It says for any constellation where the matched pairs have a positive inner product and the mismatched pairs have a negative inner product, there exists a separating hyperplane H that demonstrates the modality gap. So it has a positive inner product with the UIs and a negative inner product with the VIs. So the picture when projecting along H looks like this one, where all the text is on one side and the images on the other. Now, like what in the world is this? Well, this holds whenever the margin is bigger than this relative bias parameter, right? Because these matched pairs have inner product at least M plus B or B plus M, and these are below B minus M, and so we want kind of those two quantities to straddle zero. So this captures this shaded part of the green region. Okay. So this is unavoidable. You have to have a modality gap if you have a constellation. Constellation is equivalent to zero loss, right? So if you are getting zero loss and you're in this situation, this is maybe a weakness of our arguments, but at least if you're in this not insubstantial region, which does capture these actual industry models, then you necessarily have a modality gap. That's the theorem, and maybe I didn't read this out so well. I neglected to emphasize that there could be D points that are kind of on the wrong side. But again, we're in the regime where N is like huge. N is 10 billion and D is 1,000. So like whatever, 1,000 on the wrong side, who cares? Okay, so I think I'm gonna try to convey maybe some or most of the ideas of the proof. Yeah, we're in a math place after all. We've got lots of mathematical people here. So yeah, let's try to understand why do you have to have a modality gap? And maybe, Sasha, you can fill in the higher dimensional argument. But we'll see. It's maybe Kiril will fill in the higher dimensional argument as we speak. It's unclear. Yeah, because so far, we're just talking about modality gap being something that's in one dimension. I think in experiments, I think it is just one dimension, right, Kiril? It's that they're separated. It's not that you can find like some plane in which it's like opposite. I mean, I don't know. Anyway, we can think. I mean, yeah, it's unclear how to even define it, I think, in terms of higher dimension. Anyway, so why is there a modality gap? First off, why is this not obvious? Well, I don't know, maybe it's obvious to some of you, but it wasn't obvious to us. Maybe just to try one thing is you could take, so you're trying to find H, right? That it has a positive inner product with U's, negative inner product with V's. So you could just take, for instance, minus V1. Minus V1, well, V1 has a negative inner product with U2 through UN, right? That's the assumption here. And so minus V1 is like almost the right thing, it seems like, because it has a positive inner product with all these U's. But the issue with that is that the V's themselves are arranged in some crazy way, potentially. And so it's hard to control then that if we took this as H, that this second condition is satisfied, that there should be a negative inner product with the other V's. All right. Okay, so as a first step, let's totally forget about the V's. And let's just remind ourselves we want an H that has a positive inner product with all the UIs. So let's just think about the candidate H's. Okay, so if we think about any particular UI, the H's that are legal, that are good for us, are those that lie in this hemisphere that is with North Pole UI. So we're going to consider HI to be that hemisphere. Those are the good h's for the particular UI, that's capital HI. And so the existence of the desired h that has a positive inner product with all of them is the same as the intersection being non-empty, right? So why should the intersection be non-empty? Well, there's some wonderful fact from convex geometry called Helly's theorem that gives a sufficient condition for the intersection to be non-empty. So here there's a lot of intersections, it's an intersection of n different things, but Helly's theorem tells you that if you check that every d plus one of them, so relatively very, very few of them, has a non-empty intersection, that's enough. Then all of them together have a non-empty intersection. This uses the fact that these are convex sets. Okay, now how do we check that d plus one of them have non-empty intersection? Well, if you, for instance, just care about first d, u1 through ud, u1 through ud plus 1, well, vd plus 2, so any other v has a negative inner product with them. That's our assumption here, right? It's a mismatched pair, has a negative inner product. So that's good enough. That tells us that they have a non-empty intersection. That's an example of a vector for which all of them kind of work. So you can take minus of that thing and you have a positive inner product. So Helly's criterion is satisfied. And so the intersection is not empty. Okay, so we sort of have something that works for the u's, right? You intersect all of these hemispheres and you get something. So now how do we make this h have a negative inner product with the v's, right? Remember, we forgot about the v's, but those are kind of the whole crux. Well, a second claim is if it were the case that the h that we found here, that's in the intersection of all these hemispheres, is in the convex hull of the u's, then we'd be in good shape. Then we'd be done. Okay, so why is it that we'd be done? Well, it needs a little bit of an argument, but it's short. So consider V1. Okay, so we're gonna try to get somehow that V1 has a negative inner product with the H. And so suppose actually that H is in the convex hull not of U1 through UN, but of U2 through UN. Well, then by linearity, you just expand out the inner product, and V1 has a negative inner product with each of the components that make up H. And so you just have a kind of a conical combination of conic combination or convex combination of negative quantities, and we get the property that we want. Okay, so this step's a little subtle. It's saying if you only care about V1 and then H were in the convex hull of the rest of them, you'd be in good shape. Okay, so how is this useful? Well, if H were in the convex hull of very few things here, we'd be happy because you'd have a negative inner product against all the other V's. And that reduction is done by Kara-Theodori's theorem. So instead of H being in convex hull of U1 through UN, we can reduce it to the convex hull of I1 through ID, so just D of these. And then the point is for any other V that's not one of these, you're in good shape by this very same argument. All right. So how in the world, finally, are we going to get H into the convex hull of the U's? This part I won't actually tell you how to verify, but the intuition is that, well, let's project the H that we initially got directly onto the convex hull. I mean, it's not there. Let's just force it to be there. Why is that a useful thing? Well, the hope is that it doesn't ruin the property of being in the intersection of hemispheres. We have to maintain that property. That's the original property we wanted. And intuitively, we're moving H closer to the UI vectors by putting it in the convex hull of those things. So hopefully it doesn't ruin the property of being like, essentially close to the UIs, which is what this hemisphere property is. So that's kind of the last step, and that requires another argument that I won't go into. Okay. Turns out that this result is sharp in terms of this, except for at most D points. So Kiril and Iliyas came up with this construction that shows that there is a constellation that satisfies everything except for the fact that no matter what H you take to demonstrate the modality gap that puts UIs on one side and VIs on the other side, there are D-1 values where things aren't right in the sense that they have the same sign of projection or inner product with age. So they can't possibly, basically you have to have D of them on the wrong side. I don't know if I should explain the construction, but it's there in Kiril's brain, so you can go talk to him after. Yeah, I mean it's a nice construction. So if you're curious, yeah, worth thinking about. And then finally, let me touch back on this many modalities point that I mentioned. So people are using these things. You already have like a really good text and image model, but now you've got some video, you've got something else, you got some audio. How do you combine that? And like, what do you do? And can we say anything about that situation? So what people do is they make a graph between the modalities, and then they have a pairwise loss between each modality. It could, in principle, be a separate loss, but usually it's the same one. And so the loss would be the sum over the edges of this graph of the pairwise contrastive loss, whatever one you're using, between those. So it looks like this, and people are doing this sort of thing. And it'd be nice to, maybe at least make some of this development work also for the multi-modality case beyond 2. And so we have a little bit of work in that direction. So remember earlier the construction of this green region, it started with spherical codes, and then it kind of shifted things into this, blue part and red part to produce the MB constellations that were the ones that are zero loss, that are global minimizers. And this generalizes by replacing this last coordinate by a higher dimensional simplex. So actually, like one-dimensional, this like plus and minus is a one-dimensional simplex. So that's k minus 2. If there's 2 modalities, sorry, k minus 1, 2 modalities minus 1 gives you on the line. So that's this direction. If you have k modalities, then you can take points on the regular simplex. Do centroid as the origin. You can check that the inner products are slightly negative, and this can then be placed in the last coordinate instead of this shift. You can then have the jth modality have the jth vertex of the simplex there in the last coordinate, and the first one is still just the spherical code that we had before. And you can just compute out what the inner products are. Here, these are different modalities, so J and J prime for the same object, and you get something kind of big because the same code word showing up, so CI, inner product CI is big. And for mismatched pairs, you get something smaller because of the alpha here, so the code words are separated. So it's the same kind of reason that this construction led to loss configuration. In the 2 case, still leads to zero loss configuration in the multimodality case with these parameters. So it's maybe not something super deep with these parameters. You can compute them from this. All right, so let me wrap up. We characterized the global minimizers of SigLIP, which is this popular kind of contrastive pre-training model. We got some understanding of what SigLIP is doing. We understood that modality gap is unavoidable, at least in a big part of the parameter regime. We understood something about the dimension versus size trade-off. And there's many, many more questions and a lot left to do. So I'll end there. Thanks very much.